Good morning, everyone. Before we begin our journey, I would like to start with an acknowledgement of country. We acknowledge Aboriginal and Torres Strait Islander peoples as the traditional custodians of the lands, skies, and waterways we are on today, and we pay our respects to elders past and present. For tens of thousands of years, First Nations peoples have observed, understood, and shared knowledge of Australia's weather and climate. And their deep connections to country represent one of the longest continuous weather records on Earth, and that knowledge remains vital as we look to the future. Now, today, we are inviting you to do something a little unusual. We're inviting you to travel forward in time, not with flux capacitors or questionable paradoxes, but we're using the very best weather and climate science Australia has to offer. We'll explore the future of Australian weather and what that means for one of the biggest challenges of our time, how we power our lives. So you're joining me, Associate Professor Ailie Gallant, as we head to the year 2050 with a team of time-travelling weather and climate scientists on a guided tour of Australia's future energy and weather landscape. We're going to understand where we're going and what we're doing. It's going to help us to know who's driving this time machine. Now, I'm part of the Australian Research Council Centre of Excellence for Weather of the 21st Century, or as we like to call it, 21st Century Weather, because it's a lot to say out loud. We're a national team of weather and climate scientists who work across universities around the country, and we focus on a pretty simple idea: that global warming doesn't just change the climate, it changes the weather that we experience every day. And so traditionally, climate change gets explained through averages. Average temperature, average rainfall, and those things do matter, but it's not averages that knock out power lines. And it's not averages that overwhelm energy demand or leave us wondering why the heater went out on the coldest night of the year. What really matters there is weather. And at 21st Century Weather, we focus on weather change. So that is how climate change will influence the day-to-day weather events that affect our lives, our infrastructure, and increasingly our energy systems. We study weather on the ground, in the sky, and we study the weather systems that control it, from cold fronts to heat waves, storms, sunshine, and sea breezes. We want to understand how weather works today and how it's likely to behave in a warmer world. And Australia is a fascinating and challenging place to study this. As we increasingly rely on weather-dependent energy sources like wind, solar, and hydro, our energy system in turn becomes more weather-dependent than at any other time in history. And while we are a land of sunshine and coastal breezes, we are also highly exposed to weather extremes, from scorching heat and cold outbreaks that can strain the energy grid when demand spikes, to severe wind gusts that knock out transmission lines. Our grid is deeply exposed to the weather that drives it. So today you'll hear from scientists across our partner institutions, including Monash University, the University of New South Wales, the University of Melbourne, the Australian National University, and the University of Tasmania, all who are part of the Centre of Excellence for Weather of the 21st Century. Each speaker is going to look at a different part of this puzzle, from the weather systems to climate modelling to energy systems to human impacts, and together they're going to help us move beyond the question of what's the average future climate to questions that are far more practical and far more urgent. What kind of weather will test our energy systems the most? When will renewable energy be abundant and when will it be scarce? And how can understanding future weather help us to design a grid that is reliable and resilient? And so as we focus on weather and the energy sector, we'll tackle some big and sometimes uncomfortable questions. Specifically today, we're going to look at what's the worst case scenario for future energy grids. How will we cope with more intense heat waves, cold snaps, and longer lasting extreme events? Is wind power actually more reliable during the day, or do we have wind power accessible at night? And will solar, wind, and hydro, or some clever combination of all three, be the hero that keeps Australia's homes and businesses running? Most importantly, today is not about doom and despair. It's about understanding risk, understanding opportunity, and understanding choice. Because the better we understand future weather, the better prepared we are to make smart decisions. So, buckle up. You're the first public group to take the trip into the 21st century weather time machine. So let's dial up 2050. Please keep your hands inside the vehicle at all times. Do not touch anything outside or you'll mess up the space-time continuum. And let's get going. Okay, I hope that didn't make you all too dizzy, but we've made it to 2050, hopefully with everything still intact. Now, during this tour, we do encourage you to be curious. So at any time, please feel free to ask questions of our host using the Q&A function, which you can find down the bottom of your time travel console. However, we will leave answering those questions to the end of our tour. And before I set you loose, we will need a little bit of a briefing about what to expect. So I would like to introduce you to Dr. Doug Richardson, who is a Centre Researcher from the University of New South Wales. Doug will give you a quick orientation session before we start our tour proper, giving us important context of the national energy market, what it does, where it operates, and why you should care. So take it away, Doug.
Hi, welcome to Orientation with me, Doug. In this session, we're going to answer questions like, how do energy markets work? What is the NEM, and why should you care? At their core, energy markets are quite simple. Electricity is generated using fuels and renewable resources. That electricity is then transformed to high voltage for efficient transportation around the network before being consumed in our dwellings, homes and businesses. The national electricity market, as the name implies, is a wholesale market where energy is bought and sold by retailers onto customers. Because Australia is such a large country, we have multiple energy grids, such as these small grids in the Northern Territory, larger grids in Western Australia, and the largest grid of all, the national electricity market, which services the 6 eastern states and territories. Now, the NEM has changed fast, especially the way that we generate electricity. In 2005, we had lots of coal and gas power plants to generate our electricity and some hydropower as well. By 2026, well, we still have lots of coal and gas and some hydropower, but also lots of wind and solar power too. Now, as we sit here from our time travel machine in 2050, the amount of renewable energy we generate vastly exceeds that of fossil fuels. You can see that there's a really significant amount of energy that we generate from rooftop solar, large-scale solar, and wind power. Now, this means that sunshine and wind are very important. And the message I want to leave you with in this orientation is that if we care about electricity generated by our solar farms and our wind farms, then ultimately we care about the weather too. Orientation complete.
Thanks for that overview, Doug. So now I'm going to pass you over to Alex Dunn from Monash University and Mahara Salpadoru from the Australian National University. They'll take you through a short safety briefing. After all, we are in 2050 now, and the weather is a little different to what it was a quarter of a century ago when we started. And this has some very real implications for the energy grid and for your personal comfort. From cold snaps to heat waves, pack your puffer and a sun hat, as both Alex and Mahara will explain how future weather pushes our energy systems to its limits.
Some might say the future is like an endless summer. You've probably noticed yourself that summer heat has been getting pretty extreme. Unfortunately, the extremes get more extreme too. In the future, heat waves are hotter, more frequent, and last longer. We need to be prepared for how this will affect our energy system. Our future energy system relies heavily on variable renewable energy, such as wind and solar, which rely on the weather and vary more than traditional fossil fuels. Additionally, more rooftop solar and electric vehicles will be used by Australians, meaning consumers can influence how much energy goes into the system as well as out. The future energy system will be harder to predict if we don't work to understand the weather that will power it. If we understand how variable resources fluctuate during extreme weather events, we can coordinate the supply of electricity to meet demand. By accurately predicting supply and coordinating resources to meet demand, we can secure the power supply and prevent blackouts. Without weather-informed dispatch processes, our future energy system is very unstable. Instability in an energy system is when total load or energy demand is not equal to the supply. Both too much or too little energy supply causes negative consequences, like damage or blackouts. Heat waves affect energy demand as people switch on air conditioning and space cooling. Typically, daily energy demand looks something like this. It peaks in the early evening and is lowest around midday. A midday decrease in demand is mostly explained by the sun shining and generating millions of watts of clean, green power. If there isn't enough demand to match the boost in solar generation, large industrial electricity users are deployed to use the excess electricity. Electricity demand increases throughout the course of a heat wave, especially during the evening peak. More people come home and decide to switch their air conditioning on during a heat wave. If a few more people decide to work from home because it's hot, they can increase the daytime demand as well, although the timing and magnitude of these changes are dependent on a lot of factors, from whether it's a weekday or a weekend, it's school holidays, how hot it has been recently. Even major sports matches can affect the demand curve. The timing of changes matters because some periods are more prone to instability than others. In the late afternoon to early evening, generation drops off as the sun sets. At the same time, people are coming home and cooking their dinner. Demand skyrockets. So the operators are playing a high-risk game, trying to match demand and supply with their limited controls. This afternoon to evening period is often when the system is at the highest risk of instability. But we're missing an essential and unpredictable piece of the puzzle. The timing and amount of electricity that you can get out of a wind farm can depend on whether a cold front is passing through or whether there's a mountain nearby. That is to say, the exact quantity of the wind resource depends on many local and large-scale drivers. That means that it can look like this on one day, like this on another day, or even like this in another place. My research maps wind generation for heatwave and non-heatwave summer days. I look at how different regions experience changes to their generation during heat waves and investigate the how and why to identify environmental factors that influence the performance of Australian wind farms during heat waves. Using the generation curves that I've calculated, we can identify the times where heatwave generation is higher than the summer average and times where regional generation performs worse than the non-heatwave average. By identifying these periods, we can assess when a region might be able to store excess energy, maybe charge a battery, or when a region needs additional assistance and where it might discharge battery power. By comparing the performance of different regions, we can identify weather-related drivers that cause the generation profile to behave a certain way. We can then consider how those weather patterns might change in the future. If weather scientists, urban planners, energy providers, and market operators work together, we can plan an efficient, reliable, renewable energy system by maximizing our investments into new infrastructure. Otherwise, our future might look a bit like this. Thanks.
With more renewable technologies penetrating the grid, we're becoming more reliant on weather than ever before for energy security. You see, we need the sun shining for our solar panels to work and to charge our batteries, and the wind blowing for our turbines to run. But we also care about the weather because it changes our behaviour. Specifically, we see big fluctuations with temperature. So on a really hot day, people turn on their AC, or on a really cold day, their heater.
You might think that our biggest challenge in the future will be extreme heat days. Think back to the power system strain during the heat waves before Black Saturday. And whilst you're right, these do pose their challenges, specifically as temperatures rise with climate change and densely populated urban areas become highly susceptible due to the urban heat island effect. These days aren't actually going to be our greatest challenges.
It's days that are like these. They're cold, calm, and cloudy.
Working with the Australian energy market operator, we've identified weather systems that, when they occurred under a fossil fuel-powered system, weren't an issue. But bringing these same weather systems into a renewable saturated grid, well, that can cause significant issues like wide-scale blackouts. The conditions that we've identified are when we have multiple days of below average temperatures. We call these cold waves. Towards the middle or end of these cold waves, if we get a drop in the wind, then we can get a pretty big supply-demand gap. If these weather systems are large and they sit over multiple states of the national electricity market, then this becomes an issue because states can't share excess power with each other, an essential part of bolstering a grid.
Our research is trying to understand these conditions better so that we can answer questions like, how often do these weather systems occur? And will they change under climate change? For now, what we can say is not to be alarmed or dissuaded from a renewable technology future. These systems do seem to be quite rare, and once we get a better grasp on them, we can help build and adapt a more resilient future grid.
Thanks so much, Mahara and Alex. Looks like even videos from the future can be a little bit glitchy sometimes. So, whether it's freezing or sweltering, it looks like understanding weather risks to our energy systems are really key to keeping the lights on in the future. So, thanks, Alex and Mahara, for your insights. We're now going to shift from weather risks to weather resources. And we actually have a few people here in the time machine with us to talk to us about that. So hopefully fewer glitches moving forward. But here in 2050, wind obviously supplies a major share of Australia's electricity. But that immediately raises some important questions. So where does that wind actually come from? How consistent is it? What patterns does it have? And where does it blow? And the big question, how do we actually know all this? To help us explore those questions, we're joined by Dr. Rachel Isfording from Monash University and Dr. Andrew Brown and Dr. Claire Vincent from the University of Melbourne. And together, they're going to take us on a walk through a windy wonderland, unpacking Australia's wind resources and what they mean for the reliability of our future energy system.
Thank you so much, Ailie. You ask a lot of very important questions. So let's see if the cosmos can help us reveal the hidden truths that guide us as we work to secure Australia's wind energy reliability. Let's start with your first question. Where does wind come from? Well, at the highest, most fundamental level, wind comes from Earth constantly trying to reach a state of equilibrium or balance as it's heated by the sun. It's spinning around on its axis while also spinning around the sun. And just for simplicity's sake, a lot of chemistry happens with different gases in the atmosphere and water. And this eternal struggle for balance, which I'm sure many of us can relate to, manifests for Earth specifically as various weather systems, large-scale circulation features, and semi-predictable wind behavior around coastlines due to the temperature difference between land and atmosphere, or excuse me, land and water. And, the cosmos are telling me we'll hear about this in more detail in the very near future. So these larger scale systems also interact with smaller scale behaviors in the wind, ranging from convective updrafts that cause spotty thunderstorms, as well as small scale eddies and turbulence that are caused by the landscape features and topography. So, hopefully that answers your first question. Now we know why we have wind. But next we want to know, at the end of the day, what this means for Australia's energy security. So where do we find the best locations for wind energy? And a bit of a spoiler alert, we're tackling this through climate model benchmarking for wind energy applications. And this involves a very nested, interconnected relationship between establishing a historical baseline from our observations, as well as identifying relevant wind characteristics and processes that drive our wind energy generation, as well as comprehensive climate model assessment. So starting with the first one, establishing a historical baseline of wind behavior, we use observations from various global observation systems For wind specifically at turbine heights, we use station data that we can scale our turbine heights, wind Doppler data, which again, I'm hearing from the Cosmos we'll hear about soon, as well as satellite data and such. We can also use climate models, specifically historical climate model simulations and idealized simulations, to improve our physical understanding of the processes that drive winds and wind variability. So we have a better quantifiable context and understanding of how to study this and how winds could potentially change in the future. We also have what's called reanalysis products, which essentially combine all of our global observation systems with climate models to produce essentially a historical data set that's both physically consistent and coherent across time and space. All of these different data sets have inherent strengths and limitations, which we explore much more in climate model benchmarking and assessment in our research here at the center. Next, when we're looking to discover where to put or where to find the best locations for wind energy, we're working very closely with stakeholders to co-identify wind characteristics that are very relevant to energy generation. So we're working with them to understand their decision-making processes and essentially categorize different wind characteristics, as well as to define quantifiable metrics and methodologies to assess these different characteristics in our observations and in our climate models. And last, we bring this all together to perform a comprehensive climate model assessment of historical simulations, and then to assess uncertainties in the projections to understand again how all of these characteristics of wind could potentially change in the future. And this essentially starts with that high-level average that Ailie was mentioning we want to avoid, but this just gives us a nice big picture of what's going on in our data set, so we can see if there's anything starkly wrong. We have a data set that's too windy or might not capture higher winds over oceans and things like that. And then essentially we tunnel down into smaller scales, looking at renewable energy zones, bringing in station observations to look at finer scale processes like diurnal cycles. And then we bring all of this back to the bigger picture of how weather systems and all of the manifestations of wind interact with all of these things. So in a nutshell, with historical observations, stakeholder-informed analysis, and climate model benchmarking, we can essentially work to secure Australia's wind energy reliability, and it's a win-win for everyone. Thank you, Ailie.
Thanks. I believe we're hearing from Andrew now.
Thanks, Ailie. So, we're in the year 2050. We're on holidays in southeast Victoria, and it's a really hot day, so we've decided to head to the beach. Victoria has managed to reach their government target of 9 gigawatts of offshore wind energy. And you notice there are some wind turbines in the distance, slowly turning throughout the day. So, a perfect beach day. We've got our sun protection and we're ready to jump in the water. Later in the day, as you're thinking of heading back home, you notice the wind starts to pick up and the turbines start rotating faster. So what's going on? What you're observing is a phenomenon called the sea breeze. During the day, the land heats up more than the ocean, creating rising air over the land and low pressure, compared with sinking air and high pressure over the ocean. This causes a circulation with onshore surface winds that flow from the sea to the land and an offshore return flow above. Overnight, the reverse circulation can occur, which we call the land breeze. A wind forms near the surface, blowing from the land to the sea, although it's usually much weaker than the sea breeze. The sea breeze is a local wind phenomenon that could provide the grid with an important source of wind energy. At 21st Century Weather, we've been looking into where and when sea breezes occur and how they can contribute to wind energy resources. Using 46 years of historical weather data, we've created a data set of sea breeze occurrences around Australia. We've found that in areas where offshore wind farms might be built, winds tend to be stronger in the afternoon than in the morning due to the sea breeze circulation. This plot shows the average wind capacity factor throughout the day for our beach in southeast Victoria on summer days that we identified with sea breezes. You can think of this capacity factor as the fraction of energy a wind turbine would produce relative to its maximum capacity. You can see that the wind energy capacity peaks on average at around 5 or 6 p.m. If we plot the average energy demand for the state of Victoria on the same plot, we can see that the peak also occurs in the evening, similar to the peak in the wind cycle. This represents the time that people have got home from work or the beach and are switching on their appliances and air conditioning. So we think that sea breezes can provide an important source of wind energy in Australia that can help balance energy demand. At 21st Century Weather, we're continuing to research local winds and sea breezes in coastal areas. We are considering current and future trends in sea breezes and how this might influence Australia's energy system. Thanks for coming to our breezy beach day in the future.
Thanks, Andrew. And now on to Claire.
So it turns out that while you're asleep, the wind gets up to all sorts of mischief. Did you know that the wind speed loves to dance during the night? This wind profile, which shows the wind speed on the horizontal axis and the height on the vertical axis, is a theoretical example showing how the wind develops through a 24-hour period. This bulge of strong winds develops just above the surface during the nighttime hours. We call this bulge a jet. So does that really happen in reality outside of our mathematical theoretical example? Well, the answer is yes, but obviously not quite so beautifully in the real world. This example is for observations averaged over many nights at Ceduna in South Australia. Just like in the theoretical example, we see this pulsing and bulging of the wind doing its nighttime dance, with strong winds just above the surface. And even if we just look at one single night, for example, this one in August 2022, we can see this example of the wind reaching this maximum during the nighttime. We model this behavior of the wind in our high-resolution computer models of the atmosphere. Here's the jet getting started at about 10 o'clock at night, at around 150 to 700 meters above the surface, and reaching wind speeds of about 12 to 15 meters per second. But if you look right down at the surface, while that jet was occurring, we've got really light wind speeds. If you were at the ground, you might think it was a calm night, but if you looked up a little bit, you could see really strong winds. Perhaps that would be a really good height for a future wind turbine. Just imagine if we knew exactly when and where jets form in Australia, so we could target those heights and locations for wind turbines to generate electricity during the nighttime hours when there are no solar resources. We looked in 21st century weather at different locations across Australia where we have good observations of wind to see how often jets occur. This example is from Sydney. Here you can see winds down at the surface at 2 meters. And these are the nighttime hours here. You can see the wind gets really light during the nighttime. It's a calm, still night. But if we look upwards, then we can see that the wind actually has a maximum, or it gets really windy during the nighttime hours. So the black curves show nights when we had an observed jet, and the red curves show nights when we didn't have an observed jet. We think that jets occur on about 20% of nights, depending on which location you're looking at. We don't have much good data between the surface and 600 meters, but we know that those jet conditions must get established somewhere between the ground and 600 meters. This result can be found across Australia, from East Sale in Gippsland to Tennant Creek in the Northern Territory, where we see light winds at the surface at night time and strong winds above the surface if we look upwards a little bit. At 20th century weather, we're looking into the mysteries of these jets. We want to know more about them and how they interact with the daily cycle of the wind energy resource. When and where are the jets? How high are they relative to the heights of future wind turbines? What will jets be like in the future? And most importantly, do they happen on nights when we need to generate a lot of electricity?
Thanks, Claire. So after being out all night with Claire, it's time for us to meet Carl Durdens from the University of Melbourne, who's going to help warm things up a bit. Because in 2050, we're hoping that the sun shows up to do a lot of the heavy lifting, from charging batteries, supporting the grid, and generally keeping things running when demand peaks. But solar power isn't just about a sunny day. Where and when the sun shines matters. From a sunny afternoon to a cloudy 30-degree day in autumn, Carl is going to help us understand where Australia's best solar resources are, how they vary across the country, and what that means for the reliability of our future energy system that is built around the sun. And then once we've soaked up some rays, I'm sure many of us would like to head to the water, though not the kind you'd be hoping for after some warm sunshine. Instead, we're going to finish off talking about good old-fashioned hydroelectricity, from which many Australians, large hydro schemes like the Snowy, might feel like a constant. That first switched on in 1949, long before anybody imagined a fully renewable energy grid. But we're going to look at what hydro might look like over 100 years on from that time, and I'm going to help you answer that in our last stop of the day. But for now, I'd like you to put on your sunnies and let's hear from Carl.
Thanks, Ailie. Okay, so I'm a Centre PhD student from the University of Melbourne, and today I'm going to talk about the important role that solar energy will play in Australia's 2050 energy grid. So by this time, we have solar PV panels set up in sites all across Australia. And here this is showing the whole national electricity market that Doug introduced us before. And we can see here in these little yellow dots, all these locations where we can have future solar energy installed. And for each one of these locations, we have a unique pattern of generation determined by the local geographic coordinates and the local climate. So for example, if we imagine a site somewhere around here in northern Victoria, we can look at how the availability of solar energy on a typical average day differs both across the day and across the year. And so here what this plot is showing on that horizontal axis, the time of day, the day of the year is shown vertically, and the color is showing the capacity factor, or essentially how much generation is being produced by a solar generation site, theoretically, in this location. And we can see some interesting features, such as during the winter, obviously, we have less daylight hours, and so this distribution narrows. The sun is also lower in the sky during the winter, and so the amount of generation that we're getting in the middle of the day is lower. And then as well as these features, we can also see other impacts due to the weather, such as in this period here in the late spring, early summer, you can see some afternoon clouds coming in. And so this is just for one particular site. And what we can do is look at this type of unique fingerprint across all sites in Australia. And then we can combine them and use this to let us know how the total amount of solar energy in the entire national electricity grid will typically be at different points in time, while also thinking about this in a more regional or state-based scenarios where we can look at where different states might have a surplus or a deficit of energy. For example, the further north we go in northern Queensland, we find that actually during the winter, when they experience their dry season, they have relatively good solar. that during the Queensland summer afternoons during the wet season, they're relatively cloudy. Whereas when we go further south, the summer afternoons in places like New South Wales and South Australia has much better solar resources in the afternoon. So this gives us a good picture of what the average state is, of solar energy is like, and helps us plan and prepare for how we might use other sources such as wind and hydro to help this out. But as well as this average state, we can also better understand what will be happening on a day-to-day basis by doing this accurate short-term, rapidly updating forecasts, which we call nowcasts. This combines the standard traditional weather forecasting that we use today using our numerical weather prediction forecasts with rapidly updating high-resolution satellite imagery, which captures information both in visible wavelengths, seeing where the clouds are and how bright they are, and also in near infrared and infrared wavelengths where it can see other characteristics of the clouds and also where the moisture is in the atmosphere. And so we can take all this information, put this into machine learning models, and then use this to determine how the clouds and therefore the solar might evolve over a region over the rest of the day. And then we can further use this information to then think about how the energy generation from solar might differ from any given point in time over the next couple of hours. And this can inform lots of different sectors and help us make lots of decisions. For example, it can help the energy market operator determine where it's going to get its energy supply, it can determine households and businesses where they might get their energy from, whether they might use their own solar or instead use to charge up their batteries and use batteries in the future, and also help inform what the energy price might be over the next couple of hours. Finally, as well as understanding this average state and what any given day might look like, we also know that the climate is changing. And so for any given individual location, we can use our high resolution, up-to-date climate models, then look at how the climate might change in the future, and then what a future solar energy generation might look like, again, breaking this down by our individual sites. And so not only are we able to use our current resources effectively to help meet demand, we can also understand how this might change and how we can shore up our energy security to make sure that we're not, that we continue to make informed decisions about how we're planning our energy grid in the future. So to summarize, we use observations to help us understand the past and what this means for our electricity system. Nowcasting enables us to see what is happening in the present on a day-to-day basis, and we can use climate models to help us glimpse into the future. Thanks.
We've jumped over to Southeast Australia now. We're going to check out our hydro systems that are contributing to our national energy market. Now, these hydro systems are a small but mighty part of our energy mix here in 2050. Now, in 2050, pumped hydro is much more prolific. Snowy Hydro 2.0 was completed a couple of decades ago, and there have been a couple of other smaller schemes that have come online since that time. Now, hydro supplements our energy, and this pump version acts like a liquid battery. So it helps keep the lights on when the wind isn't blowing and the sun isn't shining. And it's our stable and dependable battery, except for the fact that here in 2050, it's probably not quite as stable as it used to be. Now, if you recall back in 2026, it had been a good 20 to 30 years since we started getting declines in cool season rainfall across much of southeastern Australia. And you can see that in the image that I've shown there with the more orange colours showing small declines in rainfall in the cooler months from around April to October. And of course, unfortunately, that's the recharge season for pretty much all the major hydro schemes in the national energy market, including in Tasmania. So this is showing the trend in total rainfall from around 1950, which is about the time that the original Snowy Hydro scheme came online, to the 2020s. But I have to tell you, even though we've had this decline in rainfall, the rain didn't just disappear. Of course it didn't. We're still a land of droughts and flooding rains, so we've continued to flip and flop between years of plenty and years of scarcity. But that drying trend has just meant that things are becoming less reliable at exactly the time of year where we're kind of counting on steady rains to recharge the hydro dams. And that's not ideal for what is supposed to be the dependable part of the energy mix. We have had wet years, and that has been great for recharge, though it hasn't been so great if it's come all at once. And it's also not been so great if we've happened to have a bushfire rip through the catchment, which, of course, with the increase in bad fire weather that we've had, has become more prevalent than it used to be. And this image really summarises the main issues that in a 2050 world we're probably grappling with. The fires, the reduction in cool season rainfall that I've already spoken about. But couple that with reductions in snow reliability and cover, which is an important contributor for some of our hydro dams. Plus, I'm not sure if some of you know about back in the 2020s, there was a bunch of evidence that the stream flow that we can yield from catchments for a given amount of rainfall was falling in some of the more southerly catchments. Now, it's still a bit messy in 2050, but that's just another issue to deal with. And of course, it's a lot drier, a lot warmer, I should say, and a bit drier than it used to be, which makes for a thirstier atmosphere. So we have to contend with that as well. And it certainly makes management of our hydro dams more of a challenge in a 2050 world. But at least we were able to work out one of the key causes of those droughts and recharge events around our hydro dams. And luckily, they were very similar things. These are these big, organised, low-pressure systems that move fairly slowly and they tend to dump rain. And that was a big leap forward in our understanding. I don't know if you all remember, about 30 years ago, because we're in 2050 this year, Warragamba Dam in Sydney nearly doubled its capacity from 42% to around 80% in just a week. And you can see that on the top image there from February 7 to February 10. We had a good look at that in the Centre of Excellence for 21st Century Weather in the 2020s, and we learned a lot about how those systems worked and how they might change in the future. And that certainly helped us to think about what we might expect moving forward. That type of information was really useful. And using that knowledge and insights we gathered along the way, we were able to think about risks to the systems in ways that we hadn't before. We could interrogate physics-based climate models and supplement them with AI techniques. And those AI techniques were new at the time, but of course they were never a silver bullet. But we could combine strengths of each and genuinely break new ground. And because rainfall and the hydroclimate remain to this day one of the most uncertain parts of the climate system, this most useful guidance came from drawing on multiple lines of evidence together. Observations where we had them, physics-based models to ensure realism, and AI to explore complex patterns. We did often wish for more surface observations, especially in those mountainous regions, but maintaining a strong physical modelling capability proved really crucial, as it allowed us to understand what the system was doing in much finer detail and to make sure that our results remained physically plausible. And that was something that mattered a lot, especially given how close we came to losing that capability in the late 2020s with the funding cuts. Our knowledge about weather driving hydropower has continued to evolve. And while hydro remains exposed to swings of climate variability and long-term climate change here in 2050, improving those understanding of the weather systems that drive dam recharge was increasingly shaping a more confident and resilient approach to managing those resources. And that was our last stop. So please take one last look at the view of 2050 and let's head back to 2026. That really does make my head spin when I look at that. I hope you're not all too dizzy. But we've travelled decades to the future. We've crossed heat waves and cold snaps. We've followed the wind, we've chased the sun, and we've checked in on our water. And along the way, you've seen how Australia's weather is changing and how deeply our energy system depends on it. And how that understanding depends on weather, not just climate, to help us manage risks, seize opportunities, and keep those lights on. And hopefully you still all have your limbs and you didn't run into a random grandchild along the way. We really tried to avoid paradoxes sneaking on board. But now that you've seen the future, we need your help. We want you to become ambassadors for Australian weather and its application to renewable energy. We'd love you to take those ideas with you and share them with your colleagues and your family and friends. But now it's time to ask questions and open the Q&A. So please feel free to put your questions in the chat in the last 5 minutes of the session, and we can do our best to answer them. Thanks very much. All right, so we have one question here from Jackie Brown. Thank you, Jackie. Around how stakeholders are responding to this information, and are they using it, and does uncertainty inhibit action, and are there other factors that stop them from using this advice? I think that's a really great question, Jackie. We are engaging with stakeholders, including AEMO and a few energy companies as well, particularly Energy Australia. Alex showed you an example of that in the work that she's doing. I think the hard part of this is at the moment, you know, the energy system is set up that there are regulators, there are market rules, there are approvals processes, and they actually don't require stakeholders to look at the science. So when our stakeholders are looking at the science, they're doing so simply because they want to make the best decisions possible, but how they make those decisions in the current framework is quite difficult. So we're looking forward to continue conversations with some of those people in the regulating and marketing environment to perhaps help bring some more science into that decision making. Thanks. I'm not sure if there's any other questions. If there are, please put them in the chat. We still have about 60 people hanging around in the Q&A. There's also some questions that have been answered, I believe. Mandy spoke about a wind resource in terms of looking at wind across the continent. And I'll just add to what Alex responded in the chat around not having that across the continent, you know, for the first time recently. I think the issue in 21st century weather is that there is information and data out there. People are certainly looking at this, but as Rachel discussed, knowing exactly what this data are showing us, you know, we can have lots of different data resources and sometimes they actually show us different things. So knowing how to use these data sources and what we kind of trust and what we think about in terms of mean wind resources, but then also looking at those fine scale resources like Claire spoke about nocturnal jets. We actually don't know much about those, sea breezes and things like that. This is why we're coming up in 21st century weather with some of these schemes to be able to detect these things and examine them to understand them a lot better into the future. We probably have time for just a couple more questions. And so Ailie Wilson, great name, Ailie, is asking in the recent summer in South Australia highlighted progressive buildup of salt and dust on power lines causing outages. Will the study consist of risk to overhead power lines in coastal regions and increased dust storms as well? So thanks, Ailie. I think we're certainly looking at these types of high impact events. We're not looking specifically at the salt and dust on transmission lines, but we are looking at those types of weather conditions that perhaps don't do so well for transmission lines like extreme winds and things like that. So we're very much concerned with the weather influences, hence the name 21st century weather, rather than the power lines themselves. Keen to know if, and Carl, thanks for your question, Carl, keen to know if 21st century weather is directly feeding into the future ISPs AEMO will produce. Carl, whether or not we're feeding into them, we're not privy to that information, but we are talking with AEMO, yes, and we have been, working with them to think about the questions that we need to ask as the Weather Centre so that they have the information that they need to make those types of decisions. So thanks very much. And yes, 1 minute to go. So Mandy, we can answer your question. Are you looking at weather influences in Australia and ocean warming? You might have to clarify that question for us, but in terms of the influence of ocean warming on weather, most definitely. This is one of the things that we want to do in the centre, or we are doing in the centre, is thinking about these, what we call influences across scale. So this is thinking about how things like ocean temperatures influence weather, and how in turn weather influences ocean temperatures, and that those back and forth feedbacks to understand really how that weather works. But with that, it's 1 o'clock. We will let you all get on with your day and get used to being back in 2026. Thank you very much, everybody, for attending. And if you have any questions, please do look up the 21st Century Weather website, 21stcenturyweather.org.au, and you can also find us on socials. Thanks very much, everybody.